My name is David Kjerrumgaard. I work for StreamNative. We're a company behind Apache Pulsar. We're also in the Apache Kafka space. Joining me today is my colleague Álvaro Rodríguez as well. So we're going to talk a little bit about everything you wanted from broker-side filtering, getting started. So we'll start with this. Nobody ever asked for data that they didn't need, right? But Kafka delivers it anyway. So every messaging team really wants the same thing, only the messages they care about. So like here's a topic with 500 distinct keys. The consumer wants just 3 of them, but the Kafka broker is dumb or naive in a way. It ships all 500 keys to the consumer and leaves the consumer to throw the rest away. Nobody asked for these other keys, but we move them anyway, and you just spend a lot of your time working on those and dropping them away. So this is just showing the keys coming in, the consumer throwing away a large percentage of these keys. So the problem is you pay full freight to deliver this data straight to the trash, right? So let's put some numbers on it. The 500 keys, this came from a use case for a financial services company where they're trying to filter out data from real-time stock tickers, right? And if you're getting 35,000 messages a second, and this consumer subscribes to only 3 of those keys because those are the keys in your particular portfolio, this means roughly 497 messages out of every 500 are discarded, assuming even key distribution, which is not a fair assumption, but nonetheless, the point's the same. Roughly 99.4% of those bytes sent to the consumers go straight to the trash. And you pay for every one of them, not once, but twice, right? You paid them to move them across the network. If you're hosted in the cloud, network egress costs money. And then again, on the CPU to deserialize them before you decide, look at them and look at the key and say, I wasn't interested in this message anyways, right? And this waste isn't an edge case, it's a default behavior for Kafka. So those wasted bytes don't cost just money, which is one, if that isn't enough reason, because we're all motivated by money, want to save money and efficiencies, but they also cost you wall clock time, right? This sort of scenario here, the same waste shows up in latency. Before your consumer can decide it doesn't want a message, it has to deserialize it. And this deserialization is a dominant cost per message, right? You have to take these bytes out, they travel over the wire as raw bytes, you convert them to Avro or JSON or whatever, you parse these things, right? And there's a cost associated with that. The consumer burns the CPU, turning these bytes into objects, checks them against the filter, and then throws most of them away anyways. So you pay this deserialization tax on these 99% of the messages, and it costs you delay in actual time wanted, right? These things back up. It takes you amount of time to process these things, right? And you never asked for this in the first place. So this isn't a new thing, right? The developers have been using messaging systems since IBM MQ back in 1994, and the developer communities all said, we want this, and this is a solved problem. So it's not an impossible problem. It's not an impossible ask, right? Every other modern messaging system has this, except for Kafka, right? So this is, JMS shipped with message selectors in 2001. That's 25 years ago. Solus ships with selectors today. Plenty of messaging systems here all have this sort of concept. So the question isn't, can this be done? The question is, why hasn't Kafka done it? And this is just kind of showing the prior art of the natural trajectory of different ways to select messages in these messaging systems, allowing developers to say, I'm only interested in these particular tickers or this particular subset of data. Right? So where you put this filter is an architectural choice, and Kafka makes the wrong one by default. So in this scenario, this diagram shows that you have the same fire hose. Conceptually, you have the same source topic. This is all the data coming from stock ticker, for example. And on the top conveyor belt there, you have your older messaging systems, right? Your JMS, your Solus. And the key is that there's a sorter, there's a filter sitting inside the broker firewall, inside that plane, that takes those gray messages that we're not interested in and kicks them out. And therefore, only the blue messages go over to the consumer, and he can keep them up because he's not overwhelmed with a bunch of garbage data that he doesn't need. On the downside, unfortunately, Kafka consuming that same firehole keeps sending these messages come in, and a lot of those gray boxes representing messages I'm not interested in show up in the queue, and they have that lag again. You're processing the messages, you have to deserialize them, and it creates this buffer. So it's a very different experience from the same data set because you're in Kafka. So the community asked for this 8 years ago, and nobody even drafted the proposal. We had the keynote about open source, and everybody wants to do these sorts of things. Just those of you not familiar with the open source Apache project, they have this concept called KIPS, or stands for Kafka Improvement Project. It's how the community sorts out what we want to do and make an improvement to the language as a whole. We all sort of meet and decide what's going to be the best solution and come up with an implementation. this KIP was filed. Basically, somebody said, hey, back in 2017, that, hey, this would be a cool thing to have. This timeline tracks the interest or lack thereof of what's happened with this. So it's been sitting there in this particular KIP 6020 for quite some time. That screenshot shows, this is probably taken a couple months ago, still unresolved, still unassigned to anybody in those red boxes, and it's last updated like in 2023. So it's just sitting there dead, right? Nothing's really happening with this, but people have wanted it. So we started with a similar, again, we started with what we could ship, and then we're aiming to expand out to the community. So as I mentioned before, we're the company behind Apache Pulsar. I'm a committer on the Apache Pulsar project. And we had a customer who wanted a very similar thing. So we started with a Pulsar, Apache Pulsar, still top level project version first, and built Pulsar SDKs around that. And then we got into the Kafka-compatible wire compatibility space. And so we've built a Kafka on Pulsar protocol handler, and we built a solution for that. And today what we're going to show you is a native Kafka SDKs. So your consumers and your producers are native Kafka. It's a drop-in replacement. And eventually on the roadmap, once we get a KIP approved, we want to move it into a full native Kafka. So we're just when the things come up again, why did you pick this particular thing that says Pulsar? It's a Kafka talk. Understand that that's our origin story. That's where we came from, and we're trying to get from point A to point B. So that's our journey, the map that we're trying to take from point A to point B. So we'll talk a little bit about the solution architecture. There's 3 layers and 3 properties that they buy you. Before we zoom in, here's the whole shape in one slide. There's an SDK on the client. There's a control plane that registers and orchestrates the filtering mechanism, and then the data plane that does the filtering itself. And the bottom 3 boxes indicate the properties that they deliver, right? So performance, resiliency, and scalability built in from this. And the next few slides are just zoom-ins on exactly how we implement this. So the 2 key components, the whole system is 2 pieces that the developer touches, plus a durable spine that makes it reliable, right? So at the highest level, there's the SDK on the consumer side. We wanted to make this lowest friction as possible. We don't want to scare people away, make them adopt a whole new concept of processing data because they want to do filtering. And then so that we have a native SDK that returns a real Kafka consumer. And so it's really a drop-in replacement. We'll show you some code here in the next couple of slides. The other side is the filtering engine, right? It's a horizontally scalable system filtering engine that sits on the broker side, not inside the broker. It's a distinction. I want to make clear nothing belongs in the broker because brokers need to be brokers. This sits in the same network zone as the broker itself. And it's a durable control plane that wires the 2 together and remembers what each consumer asks for and those types of things. So this is the 2 different parts. The first is a native Kafka SDK. So there's one for Java and there's one for Python. And we'll add it for other languages later. And you can see right here that basically you build your consumer exactly as you do today, and all you do is add one call to .selector, kind of highlighted there, where it says, the comment says only one new line to vanilla Kafka. The other one is at the very top. You do an import of our particular Kafka consumer, and that's it. Everything else, your semantics are exactly the same. You create your consumer the same, and you do your while true. Can I go over here and scroll? I cannot. I think I zoomed in too much. But basically your consumption pattern is the same. You have a Kafka consumer, you do the while polling, you pull it out, you get deserialized object, and you run it just as before. And that's your standard native SDK consumer creation pattern. Likewise, we also add the build because it's dynamic. So you can dynamically change the filters at any time. There, right? So the filters aren't fixed at startup. A call to set selector at runtime and a new predicate propagates down to the broker in about a second. And my colleague here is brave enough to do the demo live and tempt the demo gods. We'll show you that today here in a second. But the point is there's no redeploy. Like you could do this in other frameworks. Let's do like a Flink job or maybe a microservice or something. You say, I could do this in other code, but that would be a configuration change. You'd have to restart it to change, reread the filter. This allows you to send the data directly to via the SDK to change the filter dynamically. It just happens. And so the broker confirms that it's live, and the consumer never sees a half applied filter. It acknowledges this thing, and that's under the hood. You say set selector. It goes to a control topic, which is why we communicate between the SDK and the filtering engine is through a topic, because you already can publish a topic, so we can exchange metadata. So that's how we work it. And this is just an example. If you want to change things dynamically, you can have a UI and say, I want to add this. Again, back to the stock ticker thing. Hey, I bought a new security, so I want to add this one to my filter now. I don't want to tear something down and restart it. It just happens automatically for you. And this is the architecture at a glance. So this is, let's slow it down a little bit. Basically, things happen one at a time, right? So you come in, and the SDK publishes a filter request. It's a message to a topic. Our control plane, our orchestrator, reads that information, reads the request, identifies if there's already an existing filter on the topic or not. If there's not, it will create a brand new filter function. That filtering function also creates a filter topic of where it's going to be consumed from, where it's going to route the data, and sends that back to the consumer. Then the consumer connects to that topic. The filtering then starts reading from the source topic, and once it starts identifying messages that match the filter exactly, it routes those and only those messages to the filter topic. The rest are dropped, and then the Kafka consumer gets just this curated list of messages. It gets the 3 out of the 500 that it wanted, and the other 497 are dropped completely on the broker side. And that's it in a nutshell. So this is, again, that just runs in a loop, but that's the 8-step process that gets us to how the filtering works. One of the key decisions we made that every filter gets its own output topic, and this is not only, there's a lot of advantages of that, there's also historical precedent. You can do JMS, for example. You say, I want a queue with these filters, you got your own dedicated queue. And this gives you 3 different things right out of the gate that you can really anchor on. First is resilience. So again, you're a filter consumer, you want to connect, but let's say you crash. The filter stream is persisted independently, so you just reconnect and you reconsume consumption from where you left off. You don't fall behind as far as a cursor, you just have your information available. You can also tune the TTL, or how long you want to keep those messages, right? Different filters have different purposes. I want this data for I want a filter for context engineering. I want all the interactions, orders this customer had in the last hour. That's a different data set than I'm interested in, this very low or very high frequency, low data retention value data sets like stock tickers or IoT sensor data. I don't care. Messages that are 5 minutes old, I don't even care. They're actually worse for me than having fresh data. I'd rather have no data than 5 data. So you can adjust your retention policies on those topics as well. And that's the third point as well. You can resume from the latest. So because you are not trying to manipulate a cursor on an ever-moving stream that you don't have control over, it's your particular topic that's filtered for you, and you can pick up exactly where you left off, whether the earliest one, the latest one, by time, whatever you want, because it's a curated, smaller slice of that topic just for you and for your consumption alone. Very busy slide here. I'll try not to overwhelm you with a lot of these sort of things, but we've modeled it. The orchestrator is modeled on the Kubernetes pattern, right? It was our inspiration for that. So, if you've operated Kubernetes, you know this pattern. It's a reconciliation loop. The desired state is the set of selectors you've registered. The actual state is the filtered functions running, and the orchestrator continuously converges one onto the other. The state lives in what we call a table view. It's an append-only log-based concept where it reads as a key value store, so it's a compacted topic. The most recent value wins. That's what allows you to do updates dynamically. So this is my initial filter. I publish a new one. I get the updated one of that. And then there's also, from a semantic standpoint, it's a very primitive thing. You can register a filter, say this is what I'm interested in. You can modify it, as I mentioned before. I want to change this filter. I want to add a selector. I want to add a key. I want to add a message property. You can unregister. That's automatically called when you hit close to say I'm done with this topic, and then you can clean that up, and the reconciliation can clean up these topics. And then the last is a heartbeat, right? Just to let you know you're still alive, because you can require a lot of these filters. We're creating brand new topics. And so you don't want those to sit there forever and live indefinitely. So this heartbeat is a critical part of the architecture as well, to make sure that everything stays cleaned up, that sort of thing. And so this is sort of the filtering function. We have one per source topic, and this is another key benefit of what we did it there, because we found that when you can read the messages once and apply every filter in parallel, right? So you don't have to have one. It's not a one-to-one mapping that fans out here. That's one of your scalability criteria, right? So this is just showing a scenario where there's one source topic. In this case, there's like 3 or 4 different filters on it, and those that match on every individual message, you send a copy of that one out. So this example showed here, one matches, that goes out to output topic number 2. The next message come in, 2 matches, they go out to those topics, et cetera. So you can scale out independently, and alternatives like Flink or Kafka Streams, they can run on these sort of things, but they don't have the dynamic nature of this, and so it allows us to really do this thing in parallel. And you pay the deserialization costs once, and that's very, very very, very tiny cost, and then it gets amortized across all your different filters. So it really scales out very nicely at high scale. The other thing is here is that first is scale per key parallelism. Parallelism comes into play by what we call Pulsar's key shared subscription type, which guarantees ordering by per key. And we have horizontal pod autoscaling at our Pulsar functions, which is a serverless computing framework, right? And so because it can detect that a broker or a filtering is getting to 80, 90% of the CPU utilization that's shown there by the bar at the bottom, it can split its namespace and say, okay, well, I was initially processing 6 keys. I became overwhelmed, and so I can immediately split and scale up a new instance of my function, and we can split the key space and start our processing over so there's no lag. So it's a self-recovering, self-scaling mechanism here, and that all of that information is retained there. So at the client tier, you just have again a consumer, and behind the scenes, the brokering on the broker side, it's a self-scaling managed compute. You don't have to create a separate app sidecar for this. You do all that information yourself. And so this is kind of how we scale there. So I'll introduce what my friend Álvaro here is going to demo. I'll walk you through what you're going to see, and then he's going to do it. And so hopefully, so nobody gets lost. But again, because we started this as a financial services use case, this is obviously what we kind of went back to. There's going to be 3 layers, and this is going back to the roadmap slide where I said, hey, we're putting in native Kafka now, right? So we have a synthetic Kafka load generation tool that we have a license for called Shadow Traffic. It uses the native Kafka producer, and it can generate a bunch of random stock quotes. It has metadata like ticker symbols, the exchange it came from, what sector it was, and things like that. And it has, again, there's no Pulsar in here. It's 100% vanilla Kafka. In the middle is what I just showed you, our framework, which is Pulsar plus our Kafka-compatibility framework. So it is a broker-side detail. It is a 100% Kafka wire-compatible protocol, but it is not pure Kafka. It speaks Kafka, but it is not Kafka. And then on the other side, we just have the native Kafka clients, 9 of those running your native Kafka consumer, running their polling loops, pulling the data off, deserializing the information and showing you that, and that's vanilla Kafka. So we have a nice sandwich with Kafka on both ends and a Kafka-like thing in the middle, just to show you what it is. And this, the honest disclosure here, it's a wire-compatible swap. It's not the same broker. It's just a filtering running within that same Kubernetes namespace as the filter itself. What we've started up, we have a jumpstart thing. We have 9 pre-computed queries, right? We're going to start with 9 consumer slices, 1 broker topic to read from. Everything is sliced and filtered on that side, and each consumer receives only the messages it was looking for, and we'll show you that in the UI. We have an observability platform here. So shadow traffic generating the information, the KOP broker sitting in the middle, the 1 filtering function running, a multi-query application, so 9 queries going against it, and then a UI that lets us look into the filtering so you can see in real time things like what messages are coming through, what percentage of the data is getting filtered, and what the millisecond latency lag is on these particular performance on that. So this is kind of the big picture, kind of just like showing off this again. Shadow traffic sending 1 thing to 1 topic. Apple stocks hitting a couple of different queries, 1 through 9. All of them are using the Kafka SDK on the other side, 9 different consumers, and the observability platform is sort of peeking back in to the metrics and logs on those filters to say who's seeing what percentage of the data is coming through. Again, this is where the native Kafka sits. This is where the information comes from. And without that, now we're going to do the demo, and I'll hand it over to my friend, so thank you.
Let me check that everything is running. First, sorry. No. What is this? I cannot see the.
Here we go.
I cannot see the filtering running, and I don't know why. What is the terminal? I don't see the terminal. What is that? What is that? Sorry.
You tempted the demo gods, Álvaro.
The gods are not with me. Let me check. Because I think there's a problem with the filter, but I don't know where. Okay. no, yeah, I know. It's the... multi-queue. Sorry. What is this? I'm not able to make a start the Docker PS. What is this? I have a problem with the DNS for the... Every time I change network.
So I see.
It's here, it's coming.
Real-time debugging. This is always the
Sorry.
challenge. That's okay. Promise it works. We've done this before. If not, we can definitely show you afterwards on this. But the UI is going to have this running here in a second, I hope. If not, we can go back to the slides.
Yeah. Why the... We tested right before and everything was working, and now it doesn't want to start. Okay, I will start again the observability too.
Says reconnecting. That's promising.
Okay, let me check if... I think I'm having problems connecting to the server too. Let me check this. Shit. What is this coming? I'm sorry for this. Now it's coming again. Great.
We got data flowing.
I'm getting data, but the multi-queue is not working. I don't know why.
All right, we'll just move on with the slides then. That's fine.
Yeah. Now it's coming. Okay, now it's coming. Sorry for this timeout.
That's all right.
Okay. Sorry for this. Okay, I suffered a little.
Thank you.
Okay, so here we have it. We have the application running, and I need to look for my mouse now. What is my mouse? I don't know what is my mouse.
Yeah, I saw it for seconds there.
Yeah.
Calm
Do
down.
you see it? I don't see it.
Yep, it's at the top. Turn out a little bit left.
Here. Okay.
There you are. Yep.
Okay. Why it is not going up? Okay, so here. So I will create two windows to this. Okay, and I will. Why I don't see the fuck?
Go back to the UI page. It should
Okay.
show the UI.
Okay. So here we see it.
Yes.
I will start recording time here. So right now we are sending 280 messages to the broker, to one of the topics. Okay. We have this amount of filters. Well, the times right now, well, the Wi-Fi here is better than in my hotel. So this is my, the latency is end-to-end. So it's shadow traffic, try to send a message. From the moment it tries to send a message, it's put a timestamp. Then it goes to the broker, the filtering function work on it, and write it on the topic, on the exit topic. And this is the end-to-end time. So the application is checking the production time on each side. Okay. So this is since production happened till it passed the filtering. It's already in the exit of the topic. Okay. So here we can see we are sending 217 messages. I'm sending them from my laptop. This is why it was not working before. And at the beginning, in the example that David put, it was like they were only choosing 3% of the messages, no? But here we are going a little bit higher. So we are dropping only 7% of them based on the filters. Okay, so with these 9 filters, where we are choosing different things, we are choosing different keys, different sections of the message, we are dropping only 7% of the messages. Okay, so this means that we are saving almost peanuts. So we are not saving anything, but later, as each filter drop a few, then we win we saved a lot of bandwidth that get out of the brokers. Okay, so even in this case that we can have some filters that we are dropping 67, we are dropping 50, so we are sending almost everything. In that case, if we compare this with a fan out of 8 subscriptions to the same topic, we are saving a lot of bandwidth. Okay, so this is since I started talking more or less, so since 2 minutes ago, we have saved this. We have saved to the processing time, as David mentioned, with the deserializing on the consumer, because all the messages will be valid for them. In the case where we are using LLMs to process data there, we are saving data there too. And the other thing is, like, to prove that this is a network side issue, I put Python producer locally to the cluster, okay? So then I can simulate if this works. That is not the port. Check if I go here, open simulator. So why? This works, but this doesn't.
Let's just, we got 4 minutes. Let's go finish the slides.
Okay, well, let me go here and change a filter in here. So for example, if I go here, let me check if this works. Yeah, so here I can edit the filtering. If I go to the output of the topic, I can see the messages on. So each message is filtered by Meta, NVIDIA, but I can change it here in this page. And I can look for a specific key that I'm using on this producer that is collocated to the network to avoid my Wi-Fi issue, okay? So if I do this and apply it, okay, it will take a time to be applied. That is gone, that is done. So then I come here, I pick the messages. So right now it's 10:39. So here it's 9:39. Why is that 9:39? So here the key is collocated. Okay, so now I have changed the filter. It has been applied almost immediately, and I have here the new. But the important part that I want to show you is that here, the collocated latency is this one. Okay, as you can see, the latency for the other keys that are sent from my laptop are much more slower because of the network issue. When I put the producer right closer to the broker to avoid my Wi-Fi issues, then the latency drops, literally. And well, this could be variable, but it is quite stable. Okay, and if, for example, right now I want to go again to this filter, and I go to, I edit it, sorry. Is it NVIDIA or I always forget? This is why I have the pick that is not working. But, yeah, so now the filter is in place. And if I go here and I pick the message, well, I say still, well, it has stopped the collocated. Maybe it's not NVIDIA. Let me change to Meta, that I know that I'm not going to make an error there. I changed the filter. So it was dropping everything because there was nothing there. And now I should start watching Meta keys here. Okay, I can do the same, for example, for changing in price. So if I say bigger or equal than 1,000, price, bigger or equal than 1,000, nothing will happen there. Okay, so this should drop to 0 because nothing is matching. So the last price is 941, and it's 1141 here. So it's 20 seconds ago. Okay, and if I edit the price again, and I put it bigger than 0, and it's applied, then the topic will show again the messages. Okay, so now 9:42 in UTC, and we can see Meta, and the price here should be bigger than 0. Okay, so the price filter has been seen almost immediately. Okay, there is a nice point here because we have a pulsar behind the curtains. So one of the nice things that we can do, for example, apart from we have the function mesh that control the functions. Every function can have the HPA as David mentioned, and there is so you can escalate, you can increase the size of the functions with HPA. But the other interesting point here is, like, for example, if you are producing over the topic that has only one partition, okay, and I say, let's increase the number of partitions here. This is, maybe I will break the Go demo. I'm going over the limit here, but I will update the partitions. Okay, so now the idea is that the producers needs to refresh the metadata to notice that they have 2 partitions instead of 1. Okay, but once we go here and we pick, here we see that there is only P0. Okay, but if I refresh, I hope that in 30 seconds, yeah, P1 appear. Okay, so right now I have escalated almost dynamically the number of partitions without touching anything else. The filtering is working, so everything is working. The function is moved from consuming from 1 partition to 2. The producer has moved to, and the same that I have done at production, I can do it at consumption. So if there is another bottleneck because you hit the brokers is overwhelmed because this partition is having a lot of traffic, you can change it there too. Okay, so yeah, and so I think I saw.
You got more slides.
You have more slides? Okay.
You have more slides.
I have more slides. So is my side? Sorry, no, this is not what I need to show, but this is sorry.
You have more slides.
I'm always okay. Let me show you what is the other window here. Okay. So with a little bit of delay, but finally I make it to show you the demo. Okay. Why? There's no more slides.
There should be.
What is there?
There's 6 more slides.
No. Look. Okay. Yeah. Okay. Yeah. Oh, sorry. So the latency that I saw you for almost all the filters were around 100 milliseconds. When I was doing the test on my home Wi-Fi, it was 125. Okay, so but what we prove with the collocated producer is like the filtering time of the function is almost nothing. It's 1 millisecond. Almost all the time that you spend is in networking. Okay, if I showed you the Kafka Python that is producing for collocated, the P50 is 7 milliseconds already, and it was showing in the observability, it was showing 7-8 milliseconds for as a latency end to end from production till production. Okay, where it goes. So this is the explanation about the latency. We put 7 to 25. It depends in the scalability in what you have behind the curtains for the replication. Okay, but yeah, it's the filtering is the slowest. It's really low. It doesn't take too much time there. Yeah. So yeah, we put 30 milliseconds, even if it's a little bit conservative, because we hit the 7, but. yeah, in these cases, I think but in any case, the most important is not the milliseconds that you save, because it is located. The saving that you will do is it will be in the networking. That you can save a lot of bandwidth getting out of your brokers. Okay, so this is in this case you can save for the compute that we are using here. That even this function, it was really small, but this was for two cores and 8 gigabytes. Is like the bandwidth cost that you will save is massive. Okay, so we cannot do it in the broker, not to bother the broker. So we want to have the broker in a good health. So the function very close to it helps us to process it, and the network remains close all the time. Okay. Do you want to say anything, David? Here?
Nope, you're doing great.
You come here.
Yeah. This is just it. So we shipped the foundation. Yeah, thank you, Álvaro, for struggling through that. Appreciate that. I understand the pressure when things collapse. So good recovery. So we built out the basic thing, and we're thinking like what's next, right? So we got something we're pretty excited about, but there's some things we're working on in the pipeline. So what we saw was filtering based on the keys and message properties. We want to go further and do content-based routing. Let's deserialize these objects in that filter and filter by specific, individual properties within messages. That's on the roadmap next. Time window selectors, we were talking about different, I want to set this ahead of time for certain times, or we started talking about context engineering. Again, I want to find all the orders that this customer made in the last hour, or all the web clips this customer interacted with our website in the past 30 minutes. That would be a nice little chunk of time to dissect, and sort of like a pseudo query with a filter to give you that information. Things to have remote enable, disable, right? We had this UI that Álvaro was struggling a little bit to get working, but you could click, turn it on, turn it off sort of thing, to have a command that you send to say, okay, stop this, it's 5 o'clock at night, shut it down, and then in the morning, set another timer to go off in the future. And then obviously, because this is a community-focused event, we have a few ideas, but it's your turn. You tell us what other things you're thinking about would be cool to have. This is kind of a, piques people's interest, and everybody has a different use case that I haven't thought about. We started from the IoT and the fintech space. We have a one point of view, but other options are welcome. If you have any ideas, let's find me afterwards and let's talk. The code is available if you want to run it. I'll put the QR code up there for people at home. We'll share the slides. People who want to, after that smoothless demo, want to try that themselves at home, they can feel free to enjoy Álvaro's experience themselves at home. Sorry, did everybody get that? I'm sorry, it was the foams up there on that. And then just to wrap it up, thank you again, everyone, for your time and your patience with this. Hopefully, let's make broker-side filtering part of Apache Kafka, and let's work through this together. So thank you. If you need to reach out, there's our email. Thank you.
Thank you, David and Álvaro. We have time for a question or two, depending on the length. We have 2 more minutes. Yes. Okay.
Hey, thanks for that. I have one question. You said you are planning to support time-based filtering. So is that actually like a filtering concern, or are you going to somehow manage like the retention of your topics, your dynamically created filter topics to make sure that older messages are kind of, I guess, deleted from those topics before a consumer has the chance to consume from them?
Yeah, great question. So thank you for that. My initial thought was that those are two separate concerns. How long you keep the data in the filtered topic is kind of, you can control that yourself, is how long you value that. To me, time-based is cursor manipulation. We, at least in Pulsar, can go back to a certain event time and then run through that source topic from a earliest, latest, and then point in time in the middle. Then in theory put a end time, and so as you're manipulating that cursor, you could slice this between 9 and 10 o'clock. I want all the stock trades that Apple did, right, for like an auditing thing or something like that. So that's my initial thought around time-based. But if you have different ideas, I mean, again, we're open. It's something we're exploring very early. We did very primitives. This is ground zero, and things that you start building on as use cases evolve, we can see if the tool fits for sure. So thank you. Yeah.
Great.
Another
Thanks.
question or two? Or there's no time then?
I think they can meet you right
yeah, and they got to eat lunch. It's lunchtime. So.
Thank you again, David and Álvaro. Thank you very much.
Thank you. Thank you.